All right, with the jibber jabber. It is my pleasure to introduce Professor Emily Rauscher from the University of Michigan. Okay. Yes, it is. Yes. Okay. She got her PhD from Columbia back in 2010. And from there, she was awarded what was then called the Sagan Fellowship. I guess it's now all under the Hubble Fellow thing now. At the University of Arizona. We won't hold that against her. That's okay. They're a fine place. And then shortly thereafter, she moved to Princeton with that fellowship. And shortly thereafter that, in 2014, she started at the University of Michigan. Emily's won a number of prestigious awards over the years. Most recently, she's been awarded the Simons Fellowship from the Simons Foundation. And she is going to tell us about the 3D nature of planets. So we do exoplanets. And so we're learning that planets are planet-like. And it turns out that you can't treat planets as one-dimensional things, like we all like to do, but that they're round. So she's going to tell us about how that roundness affects our ability to learn about them. So take it away.
Yes, thank you, Mike. As somebody who did previously live in this state and arrived from Michigan yesterday, I understand that you all want to thank me for bringing the cooler temperatures, so you're welcome. Okay, so let's get to the science at hand. This is some visual that PowerPoint found for me and suggested, and I thought it was great because there's planets and they're three-dimensional. And it's not obvious to me that this is the solar system. I mean, like that looks like Saturn, but it looks like it's, I don't know if that's, yeah, I don't know. But it also, for the planets that I study, hot Jupiters, we need to take this and adjust it a little bit more so that we have a planet snuggled right up next to the star, because that's, spoiler alert, the type of planet I'll be talking about. Okay, so we often start talks in exoplanets by putting up a plot with a bunch of points on it that are exoplanets. I'm not going to start that way. Instead, I'm going to show you this beautiful video, which was made to celebrate crossing the 5,000 known exoplanet mark. And what you see is the night sky spread out across the entire screen. And obviously we're in the plane of our galaxy, and so we see that across the center. Once I start the movie, as it plays, and time rolls forward, you will see little circles appear where exoplanets were discovered in the sky. And the color will tell you what type of detection technique was used. But what's also fun is there's sound, and the sound you hear is scaled with the orbital period of the planet. So as this plays, it starts off with just a few little planets trickling in. And as it goes on, we're going to see them appearing more and more across the sky at a faster rate using more techniques. And you'll start to see some kind of clumpings of different planets in the sky based on the way different techniques work or the way different missions were designed. But let me pause for a second so you can just listen and enjoy. Yes, so just this beautiful way of presenting the data, right? And it really strikes home to me the fact that we now know of not just over 5,000 exoplanets, but really they're all over the sky. They're everywhere we look. And from the beautiful sounds that you heard, you already have a clue that there's quite a lot of diversity in the types of planets that are being discovered. So my favorite exoplanet happens to sit just about there. Let me pause the video. We don't need to hear it again. And if we zoom in, here you go. Now, you can't see the planet, just to make that clear. This is the star that the planet orbits around. And this star, if we take a spectrum of the star and we watch it over time, the lines in the star's spectrum will regularly shift to shorter and longer wavelengths due to its orbital motion, bringing it toward and away from us at a very regular period, which is the orbital period of the planet and star around their center of mass. And so we know that there's a planet orbiting there. We also, if we stare at the star for a while, we will, once per orbit, see the star become a little bit dimmer and then go back, and become a little bit dimmer and go back. And that's because the planet is transiting, passing between us and the star and blocking a little bit of starlight. And from that, we know how large the planet is compared to the star. So this particular planet orbits every few days around its star with a mass about that of Jupiter and a radius about that of Jupiter. And so it's Jupiter, but well within the orbit of Mercury, several stellar radii away from its host star. And so it's a type of planet called a hot Jupiter. And now if I take all of the beautiful points that were distributed in this movie, I'll put them on that plot that we're all used to looking at in this field. And so here we have the mass of the planet versus its orbital period. And we all know shorter orbital periods mean closer to the star, longer orbital periods mean far from the star. Now, you can see that we're not really down to detecting true solar system analogs yet, but we are detecting tons and tons of exoplanets, and most of them are just completely unlike anything in our solar system. And this population of planets stands out in particular. These are my buddies, the hot Jupiters, with, as I said, orbital periods of a few days and masses of about Jupiter. So the fun thing about hot Jupiters is that they are so extreme in their atmospheric physics, and they are particularly three-dimensional. I believe that all of these planets are three-dimensional, but I can get others to believe that even hot Jupiters are definitely three-dimensional. So, although it's been a more recent development, honestly, to have people believe me. Anyway, so let's talk about what we expect for the atmospheres of these planets. One is that they sit so close to their host stars that they're subject to extreme levels of irradiation, which is why they're hot. But also, because it is differential heating that drives winds on a planet, and we've cranked up the amount of heating, we also expect very fast winds on these planets, compared, for example, to Jupiter. They also are so close to their host star that we expect tidal forces from the star to have synchronized the planet so that its orbital and rotational period are the same, and it has a permanent day side and a permanent night side. This means that the heat redistribution that the winds are trying to achieve is not going from the equator to the poles like we have on the Earth and most solar system planets, but instead from the day side to the night side. Also, because of this rotational state, an orbital period of a few days means a rotational period of a few days. Jupiter is about half a day, and so these are rotating much more slowly than Jupiter. And as such, the Coriolis force, which is one of the balancing forces in atmospheric circulation, is relatively weaker. And so you expect dynamical structures like vortices or jets of wind moving all in the same direction. We expect them to be much larger. Whereas Jupiter has all those beautiful bands, Instead, you expect one or a few of these bands or jets on hot Jupiters. So just from kind of knowing the context of hot Jupiters, we can expect some extreme conditions and some rather three-dimensional, very large-scale conditions. To move beyond this, we need to solve some nonlinear equations, and so we do. This is the worst slide in the talk if you don't like equations, but I wanted to show I'm doing real physics. So in doing these three-dimensional numerical simulations of their temperature and wind structures, we need to solve fluid dynamics, which govern how the winds blow, and we need to solve some form of radiative transfer, which governs how the atmosphere is heating and cooling from the absorption of starlight and re-emission of thermal flux. So these are the versions of the equations that I use. I'm not going to go through them. I'll point out that we solve in the frame rotating with the planet. And so promise me that, or I promise you that there's a Coriolis force in that top equation, which is for horizontal momentum. For vertical momentum, we replace it, assuming hydrostatic equilibrium. We're in the bound atmosphere. We conserve mass and energy, always a good thing. And then the energy has a term where we incorporate some form of radiative transfer. And there's a few different simplified forms that we use in the community because like line by line, wavelength by wavelength, radiative transfer would be way too complicated to numerically expensive, I should say, to solve for these. When we do this, both in my group and in other groups, we tend to arrive at a fairly consistent picture of hot Jupiter circulation. And so here, instead of showing you the whole three-dimensional result, I'm choosing a horizontal slice through the atmosphere at about a pressure level. A pressure level corresponding to where emission from the planet is going to go out to space. So when we observe the planet and it's glowing, this is kind of the temperature pattern that we're seeing. So along the center is the equator of the planet. The center point is the point facing the star. And so you see, first of all, that there's a huge temperature difference between the day side and the night side, hundreds of Kelvin. You also see that there is this eastward, I don't know how well you can see the arrows, but there's an eastward equatorial jet, winds, coherent winds blowing all along the equator, all the way around. And the speed of these winds is on the order of kilometers per second. So because of these very fast winds, the circulation is able to advect some of the hot gas away from the point of high noon, the substellar point, to be a little bit east before it can cool efficiently. So this is kind of our classic pattern of hot Jupiter circulation that has existed for actually about a couple decades now. But there is extra physics that complicates this picture. And now it's important to understand that hot Jupiters aren't just a single type of planet, but in fact, they are a population of planets and they're particularly observable. So this is why I say people actually believe me that these planets are three-dimensional, because we can observe aspects of their three-dimensionality. What I'm showing here is another plot where every dot is a known exoplanet. But now what I'm showing you on the horizontal axis is the equilibrium temperature, or a global estimate of how hot the planet should be based on how far it is from the star. And then on the vertical axis is the radius of the planet. And that means that all these planets are ones that transit their star, and so we know how big they are. Now, you may notice some dim, wow, they used to look gray, now they look kind of pink to me, the points in the background. Those are known planets that are all well and good, but all of the ones that are a little bit larger and are on this color scale are ones that exceed some metric for observability. If we want to try to measure the atmospheres of these planets, the ones in the confetti colors are the ones that are more observable. And so here you see that these planets that I've circled that are Jupiter or larger and rather hot contain dozens of planets that we can actually measure atmospheric properties for. And that means that we get to observe a population, not just a single object or two. And in astronomy, where our data often aren't as good, we gain a lot from being able to see trends across a population. So I will get later into the talk in some of the methods that we use to measure atmospheres. So I will return to this diagram and some of the points, but I do want to remind you that we never actually see any of these planets, right? You see the star, but we can, all of these ones that transit, we can use tricky geometry to figure out more details about them. Okay, so they're very observable. Here is another way of seeing that. Here again, I have equilibrium temperature along the bottom. Here, a secondary property that shapes their atmospheres is their surface gravity. But now I've started labeling some of them based on ones that have been observed. So you can see the red squares are planets that were observed with the Spitzer Space Telescope before its passing. The blue diamonds are ones that were observed with JWST as of like a couple years ago, so this is out of date. The ones with the orange hearts are ones that have been observed through this ground-based technique that I'm going to talk about later, and I got tired of trying to label all of those. So apologies to Mike, who has collected a lot of the data, but I'm just going to throw down some extra points to pretend that I've labeled them correctly. So, very observable. We're using multiple techniques, multiple instruments, and I'll get to some of what we're learning with those. But the other part of this is that they're diverse, right? You notice, maybe you noticed in the last slide, you have at least a factor of 2 difference in how hot we think these atmospheres are. And that's going to change the physics, and especially the 3-dimensional physics that shapes their atmosphere across this population. So today, I'm just going to highlight a couple different processes, and there are other ones that matter, but I'm just going to highlight kind of for digestibility 2. So at the cooler end of the population, we expect clouds to form and shape their atmospheres. These are not water clouds. These are like minerals. So weird, wacky clouds. Fun, but eventually you get hot enough that maybe you don't worry about clouds so much. At the hotter end, some of these are so hot that there's some thermal ionization in the circulation level of the atmosphere. And that means that you have to start worrying about magnetic effects. Awkward. You may also notice, though, that these physical processes shape different ends of the population, and some of our observational techniques seem to have some preference too. So down here, you may notice kind of your eye is perhaps drawn to more JWST observed planets down here. JWST is also getting some of these big hot ones, but a particular advantage of this new infrared space telescope is that it lets us push to cooler planets than were previously accessible. And likewise, for observational reasons, a lot of the ground-based techniques I'm going to tell you about is preferentially getting some of the hotter ones. So in this talk, I will be describing to you a couple examples of how hot Jupiters are 3D, the physics that's shaping them, and a couple examples of how we observe that 3-dimensionality. So we'll start at the cool end of the population and talk about clouds, and I'll give you an example of how we're learning about clouds with JWST. And then we'll move to the hot end, and I'll talk about this magnetic effects ickiness and what we're learning about some of these planets with high resolution cross correlation spectroscopy. Okay. So we start with clouds in JWST, and all the faculty in here know that really I'm not talking about stuff I'm doing behind a computer, but stuff folks in my group or who were previously in my group are doing. And so I want to give credit in particular to Michael Roman, who hasn't been in my group for quite a while, but he was a postdoc with me and he introduced clouds into our group's model. And Isaac Malski recently finished his PhD with me and has contributed a lot towards studying these clouds as well. Okay. Oh, this particular planet, WASP 43b, is going to be one of the examples that I start with in terms of what we're doing with JWST. And this particular planet, it has been interesting to us for a while. And it's been interesting to us because it seems to have a very dim night side. How do we know that? Well, we know that using this technique called phase curves, where we're staring at the combined light from the planet and the star, and we know that the planet is orbiting the star. And during one part of the orbit, the planet will block some starlight, but then half an orbit later, the planet goes behind the star, and now we only see starlight. So everything above that level during eclipse is emission from the planet. And we can see that we get more emission from the planet when the day side is facing us and less emission from the planet when the night side is facing us. And so measuring a phase curve is telling us about how bright the day side is compared to the night side. For this planet, it was first observed with a phase curve using the Hubble Space Telescope. And this is the phase curve that was measured. So off the bottom of this plot is the transit when the planet goes in front of the star. Here in the center of the plot is where the planet is behind the star in eclipse. And so everything above the dashed line is emission from the planet. And you can see there is in fact a bright day side, but the night side has practically no emission. Now Hubble observes these observations were at optical near-infrared wavelengths. And so something has to glow quite hot to be able to observe it. But even still, this night side is suspiciously cool. When people ran three-dimensional models of this planet, because you have such fast winds, you do expect there to be some heat transport to the night side, enough that you should see a little bit of a glow, and you don't. And so folks said, hey, what about if it's a cloudy night side? That would trap the heat, trap the emission, and might make the night side seem dimmer. So folks went and followed up, getting Spitzer Space Telescope phase curves of this planet. And here's what those data look like. Again, the eclipse would be right at the middle. And so all of this has been normalized. So everything above zero is flux from the planet. And now there's a bunch of lines. These are models run by Mike Roman of this planet, including different sorts of clouds and using different assumptions about those clouds. And you can see that the data are consistent with cloudy models. We don't have any clear models here, but they would have way too bright the night side. So good evidence for the night side of this planet being cloudy, but then along comes JWST. And this was the first hot Jupiter observed in a phase curve with JWST. And I'm still showing you the Spitzer data because I'm going to transition to the JWST data so you can see how beautiful and wonderful they are. Are you ready? Okay, here we go. Spitzer, JWST. Oh, so beautiful, so beautiful. Very clearly see. Now we have the day side, and then circling around to the night side, the transit is off the bottom, and then circling around a second observation around the day side. And there's definitely emission from the night side that we're seeing with JWST. And the really nice thing is that we're not just measuring how bright the planet is, different sides of the planet, but these are also spectroscopic measurements. And so forgive the funny way that we show data where we have the planet flux relative to the star's flux. I'm sorry, but just trust me, this is beautiful. We're measuring a spectrum of the day side, a spectrum of the night side. And these dotted lines are the lines you would have if there were no spectral features in the planet's spectrum. And the data are distinctly different from those. We're measuring spectral features, signatures of molecules in the atmosphere. So what do we learn? Well, let's put aside the spectra for a second and just look at the phase curve integrated across the observation, all wavelengths. So here you see in black the data, no error bars, but they're teeny tiny. And this was a community effort. And so there's actually a handful of different groups around the world that contributed 3D models, GCMs, of this planet, both clear and cloudy versions. And it's a bit apples and oranges. They're not super consistent. Different groups made different assumptions. In some ways, this is an accidental model intercomparison. And the different model predictions are color-coded by the ones without clouds in the pink and the ones with clouds in the blue. And you see, again, that models without clouds produce too bright of a night side. And so we prefer the models with clouds, but you also certainly notice that not all of the cloudy models equally well fit the data, right? So now let's add back the information we get from the spectra. If we look at the day side of the planet and we look at its spectrum, here now we're showing brightness temperature. If this isn't one of your favorite units or ways of expressing information, I'm sorry. If it was flat, we'd have no spectral features. But we see wiggles, which means we're detecting spectral features. And we have, in comparison, kind of the best fit model from each group. And the dotted ones are clear models. The solid lines are cloudy models. And you notice both the clear and cloudy models have these spectral features because both models say the day side of this planet should be clear. It's warm enough, it should be clear. It should not have clouds. In contrast, if we look at the spectrum emitted by the night side of the planet, you see that the data are much flatter. And what do clouds do? They typically flatten out your spectrum. So here, the clear models are both too bright, but also have large spectral features that are inconsistent with the data. The cloudy models are dimmer and much flatter. None of them actually fit the data though, do they? It's very tricky. Sorry, we'll keep working at it. Why is it so tricky? Why are clouds so tricky? Well, there's, does anybody in the room like study clouds more locally? Sort of, okay. So you can back me up on this. Clouds are tricky. Here's an example of a literal textbook image of cloud formation in Jupiter. And so here's Jupiter's temperature versus altitude or pressure profile. And so as you move up in the atmosphere of Jupiter, you get cool enough that one species, whichever one this is, it's labeled somewhere, condenses and forms clouds. It was gas form here, now it's solid or liquid. You go a little cooler, another species forms into solid or liquid particles, etc. Right? That's how clouds form. You have material containing this species, and it moves to a cool enough region that it condenses. Jupiter is fairly uniform in its temperature structure around the planet. Hot Jupiters are not. So if I show you a hot Jupiter temperature pressure profiles, you see what I said before, hundreds of Kelvin difference between the hot profiles on the day side and the cool profiles on the night side. And you can see some condensation curves for species that might condense at these very hot temperatures. And so where the clouds are forming is really very different around the planet, where the hottest parts of the day side could be completely clear, whereas the night side might be able to form even some species that don't exist elsewhere on the planet because it's cold enough. So it's tricky and it's complicated. It's also complicated because we're not entirely sure that these are the right species, because clouds are also intrinsically a microphysical process where their formation and growth depends on the details of how little bits of things stick to each other and grow larger and maybe gravitationally settle and maybe get mixed back up. And so, yeah, it's a little bit hard. We're not completely uninformed. We do think that these minerals should transition between gas and dust or solid form around these temperatures, but we're not entirely sure. We also don't know how well they should be vertically mixed in the atmosphere. So even though they form where the temperature profile crosses the condensation curve, maybe they just exist as a little short cloud deck there, or maybe they're more extensively mixed up through the atmosphere. That depends on details that are subgrid physics, smaller than we're predicting in these large scale models. And then there's many other things too. The list of things that make clouds complicated never ends. I took this out an airplane window last month, not coming here, too much water on the ground. But here are water clouds in our atmosphere. And here you see where the condensation point for the water is, right? Here's your cloud deck. Beautiful, except why are there clouds down here? There's not supposed to be clouds down there. And why are there clouds way up there? There's not supposed to be clouds way up there. So obviously, the way that I'm framing this is oversimplifying some of the way that clouds actually work, because they scale from microphysical to really global scales in their physics. But let's just first go forward the best we can do. So we can test some of these assumptions that we need to bake into the 3D models to make them work. And here is a grid of models for planets at a bunch of increasing temperatures, so more and more irradiated by the star. And these are maps, like I showed before, where the point facing the star is at the center. The kind of dark blue purpley colors are regions that are fairly clear. And then as you go increasingly white, it becomes increasingly cloudy. And so what you see is at the cooler end of the hot Jupiter population, you can form clouds all over the entire planet. But as you move to warmer and warmer temperatures, the day sides get hot enough that the clouds burn off. Okay, but if we make a different assumption about the clouds, about how vertically extended they are, you get different cloud patterns. And if we make a different assumption about, I don't remember which species exist, you get different cloud patterns. And if you make a different assumption about how much of the condensable material actually forms into clouds, you get different cloud patterns. So this is both good and bad news, because it's bad news, we don't know what's going on, but it's good news because these would look different in observations. And so hopefully we could use observations to try to differentiate between them. Regardless, they become clear on the day side. I'm supposed to stop talking in like 10 minutes? Okay. I won't run too over, I won't listen to him. But I'm gonna skip over something. Let's jump to magnetism and high resolution spectroscopy now. Their faces are bigger than mine. This is amazing. So Haley Belts graduated a couple of years ago from my group with her PhD. And Leonard Ben Suisse is a current postdoc in my group whose last name I struggle with pronouncing. But they have both worked on this topic, so I'm highlighting their work and some planets. Okay, so Here's the ground-based technique, where if you've ever seen Mike here go like this with his fingers, he's talking about this technique. And this technique, again, we can't see the planet separate from the star, but the planet is orbiting, kind of by definition. And so the planet's spectrum relative to the star and relative to the Earth's atmosphere that we have to look through and its imprint on our observations, the planet's spectrum is going to be Doppler shifted back and forth in time. And so if you observe for part of a planet's orbit, you can try to pull out the signal of the planet due to that orbital motion. We call it high resolution because our spectrographs are, one of the main properties of our spectrographs is their resolution, which tells you how finely you're sampling wavelength, delta lambda. And Doppler shifts are also related to how much you're shifting lambda. And so we can correspond a resolution to a velocity precision. And our high resolution instruments are sensitive to velocities from maybe 10 kilometers per second down to even 3 kilometers per second. Orbital motion of the hot Jupiters is about 100 kilometers per second. And so that's how we're able to pull out the signal. Well, that's one of the many things required. But the really cool thing for me is that at the highest resolutions, that means that we're also becoming sensitive to atmospheric motion. The winds are kilometer per second speeds, often more than a few kilometer per second speeds. And the rotational velocities are also similarly large. So this technique is a little bit of a younger technique, relatively. It was first used, it can be used anytime the planet's orbiting, which is always. It was first used during a transit observation, so you still get that orbital motion. And when it was used, in addition to detecting the planet, there was a residual, after you take off the orbital motion, residual blue shift on the order of 2 kilometers per second. And a blue shift is motion toward you. And during transit, the night side is facing you. And so this was interpreted as winds blowing from the day side to the night side of the planet. Now, this actually seemed a little too slow. Our wind speeds are faster than this. And one thing that we expect to happen that would slow down the wind speeds are my threatened magnetic effects. And the basic idea is that once you have some ionization in your atmosphere, you have ions embedded in your winds, the ions are going to be blowing around the planet with the winds. If the planet has a deep-seated magnetic field, like we think planets generally do, then the winds are trying to drag ions across magnetic field lines, which if you know even a little bit of E&M is like not great. And so there's a reaction against this that acts sort of like a drag on the winds. And it's going to depend on the amount of ionization in the atmosphere, which, because of your hundreds of Kelvin difference between day and night side, you have something like 10 orders of magnitude difference between the resistivity on your day side and night side, or conductivity on your day side and night side. So magnetic effects can really shape the day side and should never really shape the night side. And so one way this might look is that instead of our standard hot Jupiter circulation pattern on the left here, on the right, you cut off that equatorial jet, you force the winds up and over the poles, and so you change the shape of the circulation in addition to changing the strength of the winds. Inspired by that initial measurement, Eliza Kempton and I said, okay, well, would this explain your 2 kilometer per second blue shift? And so I ran a 3D model with or without different drag and different assumptions. Eliza calculated some simulated spectra from it. And the models without any Doppler shifts, the model is shown as this black spectrum. And you can see all of our models with Doppler shifts are a little bit shorter wavelength, a little bit blue shifted. But 10 kilometers per second blue shift is that dashed line. So no, our models didn't, well, actually, sorry, they sort of explain it, but models with or without drag are both sort of consistent with this result. You end up observing less Doppler shift because of geometry. But one thing that we thought was really cool is that if, instead of trying to look at the overall Doppler shift of the spectrum, if you look at individual lines, then lines that are stronger are coming from higher in the atmosphere, and lines that are weaker are coming from deeper in the atmosphere for radiative transfer reasons. And because you have a 3D circulation pattern, the Doppler shifts you get at different levels of the atmosphere might be different. And so here you can see line strength, which tracks with pressure. So this is higher in the atmosphere and then lower in the atmosphere versus the net Doppler shift of individual lines. And you expect different wind shears, vertical wind shears, based on these different assumptions. And very recently, with a newer instrument and a hotter planet, Aurora Kessely led this beautiful work where these are all lines due to iron, which exists in gas phase in this planet. And she separated the lines that were strong. This is just a template. This is not a measured spectrum, but she figured out where the strong, medium, and weak lines should be in wavelength. And she analyzed the data separately for the strong, medium, and weak lines. And she found strong, medium, and weak lines. It's kind of noisy, but they're statistically significant. With, as you move to weaker lines, you get increasingly blue shifted. Now, we compared against 3D models, and none of the 3D models matched, but this sort of is consistent with our early expectation of magnetic drag. Okay, I'm gonna try to get to one more thing, which is if we think about the emission from the planet, so now we're going back to thinking about phase curves, the emission from the planet, but at high resolution, with all these Doppler shifts, it's really complicated. So here's a 3D simulation, and you're seeing the temperature structure as the planet's rotating around during its orbit and line of sight velocities on top due to both winds and rotation. And then the spectrum of the planet for each orientation. And of course, the day side is brighter, but also the spectral lines are changing as different regions of the planet rotate into view. The dashed lines contain no Doppler shifts. So if you focus on those to start, you'll see that at the night side, they're in absorption, and in the day side, they flip to emission. So you're seeing different temperature structure around the planet. The solid line do have Doppler shifts. And so if you look at that relative to the dashed line, you see that the lines are being Doppler shifted, sometimes red shifted, sometimes blue shifted as the planet rotates around. So quite a lot of information if we could access it. And different information maybe in different species. This is too much information, so just trust me when I'm going to tell you what each means. Here's a temperature map of what the planet might look like at some phase. This is saying the abundance of carbon monoxide varies across the planet because of temperature differences. So does the abundance of water across the planet. These are two of the things we're observing. That means we're seeing to different depths in the atmosphere, depending on which region of the planet we're looking at, in both water and carbon monoxide, and they're different between the two. So it's really complicated where we're getting all these photons in and how to interpret it. Remember how we can get different wind speeds at different depths of the atmosphere? Well, if you do these high resolution spectroscopy measurements, thanks, Mike, for getting these data, then you can separate your detection based on which species you're looking for in your data. And this is a way that we have of plotting kind of the velocity space of the detections. And the point is that these different blobs don't sit exactly on top of each other. So the carbon monoxide lines may have a slightly different atmospheric shift than the water lines. which somehow is encoding three-dimensional information in a way that's very tricky to pull out. Also, Peter Smith found a similar differentiation in velocities in his recent paper. Okay, this last bit is for the experts in the audience. If your brain needs a little bit of a break, ignore this and I'll call you back to me in just a second, okay? So this is work led by Leonard, who I said is a postdoc in my group. He took a three-dimensional model, got simulated spectra for it, embedded it into a simulated observation with all the complicated things that happen, and then pretended to do a retrieval on that data using just a one-dimensional model, meaning just a single temperature pressure profile. And this yellow curve is the answer compared to this kind of gray swath of ranges, which are all the different temperature pressure profiles for the region of the planet in view. Now, the carbon monoxide is coming from this pressure region marked in red, and the abundance seems not bad. The water is coming from the region marked in blue, and the water abundance seems not bad. We're not concerned about differences down here because we're not observing that part of the atmosphere. We can't see it, but we can still make functions that extend as far as we like. So it looks bad. It looks like our temperature pressure profile in the blue and red regions is not super representative of the model itself, except that this technique is measuring strength of spectral features, not the overall brightness of the planet. And so if we look at the temperature pressure profiles and now color code them with how strong our temperature gradients are, which is related to how strong our spectral features will be, you see that in the blue region and in the red region, the fit profile actually is locking on to the regions with the strongest temperature gradients. So in that sense, it actually is doing a really good job. We just have to think about it in a more nuanced way. Okay, if you fell asleep, you can now wake back up. The eagle-eyed among you may have noticed that even though I talked about clouds and magnetic effects as operating at different regions of the population, there's quite a large space where both of them may be involved. Beautiful modeling by somebody in my group that's appearing on arXiv on Friday, modeled planets across this regime, including both. Thomas did the modeling. He created all these things. He looked at the slight differences between versions with just clouds and versions with clouds and magnets, and there are little changes, and they might be observable. And so they both have thermal feedback with the atmosphere. And we have some spectra that we're trying to make sense of, but they don't. Sorry for super abbreviating that last bit of work, but I don't want to exceed my time. So my summaries are that hot Jupiters are an extreme physical regime, but also a diverse and observable population of planets. And we can study how these different interesting bits of three-dimensional physics shape their structure, and we can apply very interesting observational techniques to try to actually pin down some of these complex details. And these are the folks currently in my group. Thank you.
Thank you, Emily. You blew my mind. Questions? Christian, I think that's you.
Hold on. We need it for Zoom. They can hear you.
Thank you. This was a great talk, especially for me as a member of the Flat Exoplanet Society. But as a result of all these different extreme conditions, like the clouds and the magnetism, what can we assume these planets to be elementally and isotopically homogeneous? Or are these going to have effects on distributing certain materials in different areas of the planet?
Yeah, so I didn't focus on it a super amount, but we do expect kind of the local abundances of different chemicals, meaning molecules and such, to vary around the planet for sure. We would like to think, we have reason to think that the entire planet has some inventory of each amount of element in the periodic table, but the way that those elements combine to form water or carbon monoxide or methane or what have you will depend on local temperature and pressure conditions if you're in chemical equilibrium, but you're not because you're mixing material around. And also when you form clouds, you're removing some of those atoms into the cloud species, and so they're no longer in the gas form. And then you also have havoc from the star. Ultraviolet light can break apart molecules and induce photochemistry in the upper atmosphere. It's mayhem.
Hillary?
Thank you for a cool talk. So given all of the mayhem involved in cloud physics, if you could add one piece of the cloud physics that you think would help, what would it be?
I think I would most appreciate, so I think if we want to compare to data, we want to understand the actual sizes and shapes of the cloud particles better, like whether they're fractal or fluffy, or probably they're not just spheres, but we wish we could treat them that way and it doesn't work. But I think for me, for my 3D models, what I would most love would be for microphysics to tell me a parameterization I can use so that I know kind of where and when what should form. I know, it's so hard.
Hi. Oh, wow, that was really loud. My question is, because these are so close to their host star, is it possible that they're getting a lot of blow off from solar storms, or do they have a strong enough magnetic field that they're trapping everything in?
Yeah, it's a great question. So the interaction between particles coming off the star, I think that's what you're talking about, like solar wind kind of thing. So those probably, if they matter for hot Jupiters, only matter at really the lowest pressures, extended atmosphere, where you may have like evaporation to space, not at the levels that I care about. I'm assuming these planets have magnetic fields. There's good reason to expect them to have magnetic fields. We do in exoplanets worry more about smaller, closer to terrestrial planets, which may have a harder time holding on to maybe magnetic fields, but by which I mean generating, I know physics a bit, but also have a harder time holding on to atmospheres. And so they're like stripping by the star is maybe more of a concern.
Maybe a related question. I'm curious about how these magnetic fields get seeded in these, given that I think you mentioned that they were expected to be sort of tidally locked.
Mm-hmm.
Are they rotating fast enough that they can sort of generate a large scale magnetic field?
Yeah, it's a good question, because initially people weren't as sure because, right, so the idea is to have a dynamo to generate a magnetic field, you think you need rotation and kind of overturning from heat transport, right? And sure, we've got the heat transport, no problem, but the thought was maybe if you use scaling relations for kind of dynamo strength and theories related to that, at some point there was a thought that maybe if you start rotating too slowly, you can't generate a dynamo. But more careful work about hot Jupiters since then seems to indicate that actually they are rotating enough, even though not super fast, that it should be okay. And there's also some indirect pieces of evidence, other pieces of evidence that the planets have magnetic fields. For example, planet-star interactions, where you see kind of magnetic effects on the star, perhaps induced by the planet's magnetic field.
I was going to ask if they're close enough in radius to actually have those magnetic fields interacting.
Yeah.
Cool.
Oh, and you should ask Eugenia about that. She's worked on that.
We have a question online. Does thermal ionization of gas affect cloud particles?
Yes, probably. Do I know how? No. Sorry, that's my answer. That's the best I can do. It's a great question. It just makes me cry.
So when you're observing atmospheres this remotely, what do you define as the atmosphere versus the surface? Like where are you putting those lines?
We're not always sure. So for these planets, I mean, they're gas giants, so they don't really have a surface per se, but there's still kind of a pressure reference point where the planet becomes completely opaque to whatever wavelength you would look at, right?
So it's more like you can no longer see that it's the atmosphere. So you're saying so is it like not atmosphere and atmosphere? Or
there's no good boundary between the atmosphere and interior, but eventually it becomes completely optically thick. And so there's no photons that are going to get to us from some deeper level in the planet.
Any other questions more online?
Yes. How do you choose the various gas species and their abundance for the clouds?
All the hard questions. So we usually, we don't know what astronomers call the metallicity of the atmosphere, which means the abundances of everything beyond helium compared to hydrogen and helium. So we usually start by assuming the same relative abundances of elements as we see in the sun. And then perhaps we enhance all those ones heavier than helium by some factor that we choose. A lot of the measurements folks are making of exoplanet atmospheres are trying to get at what that metallicity is. And sometimes like relative abundances between elements themselves, carbon versus oxygen. So when we run the 3D models, we don't know. And so we should, and sometimes do, try testing different abundances. And to first order, this will just increase or decrease the amount of clouds by the same amount, because you're adding more of the material that can form into clouds. But really, it's microphysics, and who knows?
That was a great talk. Now, I don't study exoplanets, so I'm curious, are hot Jupiters easy to make? Are they inevitable? Like, did our solar system have one, but it got swallowed, or is it for a certain type of star?
So this is the age-old question. The first exoplanet that was discovered around a sun-like star was a hot Jupiter. The first one that was observed to transit was a hot Jupiter. They're not intrinsically super common. They're just really easy to find, which is how we know so many of them. But from the beginning, folks have been confused to see them there because they definitely don't match any of our theories of planet formation based on the solar system. So it's still a bit of an open mystery. People think that either the hot Jupiters formed farther out in the disk around their star and then migrated in the disk toward the star, stopping before plummeting into the star. And there's ways that you might be able to stop it. Or they formed farther out, and then after the gas disk was gone from which they formed, gravitational interactions with other objects could have kicked them onto very eccentric orbits, and then tidal forces circularized them down onto their short orbits. A few people dare to say they might have actually formed in situ, but then you're passing the buck because you now need to explain how you got so much material so close to the star with a fast enough rate to form a planet there.
Good answer. I mean, you could also wonder if our solar system didn't have a Saturn, Jupiter had become a hot Jupiter. Whole grand tack business going on. So, all right. Well, let's thank Emily again and thank her for bringing in the cooler weather.